Okay, so we've now established what the Hamiltonian is that describes the motion of the ions in the trap, and we have the Hamiltonian describing the interaction of the laser with the ions. We now have everything we need to look at how the different DiVincenzo criteria are satisfied. First, we're going to consider initialization. And initialization of the qubits is done in essentially two steps. So first is cooling. We're going to do this with Doppler cooling and sideband cooling. And then we're also going to need to do some optical pumping to sort of clean up the state. And I'll show you what I mean by that. But the first thing to look at here is Doppler cooling. Some of you may already be familiar with Doppler cooling, but likely not all of you. I'm just going to go over it briefly. So we have our ion in the traps originally, and they still have some energy to them, like a decent amount of energy. What does that mean? A decent amount of energy. So the motional state is still fairly excited. So if we have our ion, and let's just consider it, again, moving in one axis, positive Z axis. So we will take some laser, we're going to shine it, my flashlight there, shine a laser in this direction, and the frequency of this laser is going to be the frequency of the qubit minus some small amount. So it's slightly less than the frequency of the qubit. So I guess frequency of the ion. If the ion is moving away from the laser, the Doppler shift will then be such that the frequency of the laser it experiences is slightly less than this amount. So we'll say it's 2 of these small deviations. So the laser won't interact with the ion. However, if the ion's moving towards the laser, the Doppler shift will be experienced in the other way. And so now the frequency of the laser will match that of the qubit, and the qubit is going to absorb the photon. So why does that help cool the system? Well, it helps cool the system because of conservation of momentum. So the photon is coming this way, the ion's coming that way. The ion absorbs the photon. Now its motion towards the laser is decreased. So it's traveling slower. But at some point, the ion is going to have to re-emit that photon. If it re-emits the photon in this direction, because of conservation of momentum, it's going to get a boost, so it's going to get a kick going back in the direction it was already going, and it'll go back to its original motion. However, if it emits the photon in this direction, back towards the laser, then it will take its original momentum that was going in this way, minus this small kick that way, and now it's moving more slowly in the same direction. So the ion has slowed down. So depending on which way the photon is emitted, there's a 50% chance that the ion slows down, and so the system gets cooled. Now this is all sort of a simplification in one dimension, but it's the same principle that holds in multiple dimensions of how Doppler cooling works. Now obviously Doppler cooling has some inherent limit to it. When you eventually get to the point where the Okay, I'll say it like this. The ion's never going to stop moving entirely from Doppler cooling. Because at some point, it's going to re-emit the photon after it's absorbed it, and it's going to get a little kick in some direction. So there's some fundamental limit that exists to how far Doppler cooling can cool a system. That's when we turn to sideband cooling. So, actually, I'll do it, yeah. So with sideband cooling, we've now gotten to the point where the system has been cooled enough that the resolution is there for the phonon states. So we can describe our system in terms of its qubit state and its phonon motional state. So our system is, say, in some state like this. We have 3 laser pulses we can choose from. So we have a red, a blue, and then the one that's on resonance. If we use a red sideband pulse, it's going to create the transition to this state. And now we just wait for spontaneous emission to occur. And in doing so this was from a red sideband pulse. This is from spontaneous emission. Okay? And we repeat this process again and again till we get to our absolute ground state. Okay, so why do we need optical pumping, and sort of what's different between this and what's done in practice? So in practice, doing the process like this would actually be very impractical and would take a very long time. Why is that? Well, remember, a good ground and excited state are ones which are stable. So we want at least somewhat stable excited state. If the state is stable, so it has a long lifetime, we're going to have to wait a very long time for spontaneous emission to occur. So what does this look like then in practice? Well, I'm going to draw an energy band diagram here, an energy level diagram. And this is actually one for a calcium ion. And we have some ground state. I won't label all the energy levels of all the states. This figure is in the text, so you can refer to it if you like. I made this first energy level just wider. I mean, there's no reason for that, just besides making the picture easier to draw. Okay. And this state here is our excited state. So in theory, based on this process, what we would do is there would be some transition where we do a red sideband pulse, the ground state would be excited to the excited state, and the phonon mode would decrease by 1. However, the state would sort of be stuck here because of the long lifetime. So we use a second pulse to transition to this state over here that's not stable. This state has a very short lifetime, and it spontaneously decays. So we add this sort of middleman to speed up the process. Now, where does optical pumping come in? Well, ideally, spontaneous emission just occurs between this excited state and the ground state. However, it's possible that the state emits to different energy levels. If it does, we then need an additional laser to pump it back up to this state. It could be this one here, but just in practice, what it looks like for calcium is we pump it back up to this state, and then spontaneous emission occurs. So this sort of stops the cycle from breaking. So that's how initialization is done with trapped ions. So now we're going to consider how qubit control is done, starting with single qubit gates. As I mentioned before, how single qubit gates are done will depend on the type of qubit that we're using. So with optical qubits, we're just going to use Rabi oscillations. We can do this by setting the frequency of the laser to that of the qubit. So I mean, that's fairly straightforward. And it's similar to the types of single qubit control gates that we've seen in NMR and in superconducting qubits. However, for hyperfine qubits, we run into a bit of an issue. And that's that the gap between the ground and excited state is in the microwave range. And so microwaves have a wavelength of about a centimeter. So why is that an issue? Well, that's much larger than the size of an ion. So it becomes difficult to address one ion without also addressing the other ions. So one approach to dealing with this is to have our excited state, to have our ground state, have our excited state, draw it over here, and then to take some intermediary state where the gap in the energy levels is much larger, couple these states, and then couple these states. And then we have an indirect interaction, or an indirect coupling, between the ground and the excited state. To avoid resonant excitations, so to avoid the state getting stuck in this intermediary state, we detune the laser slightly. So we'd actually couple it just below it. And that decreases the probability of a state staying in this E tilde. So the issue, though, of crosstalk, is still a concern. And so there's different ways that we can address crosstalk. And just to be clear, crosstalk being the effect where you try to control one qubit and then you unintentionally have some effect on the neighboring qubits. So strategies for crosstalk. Well, one is that the lasers will go through lenses to help focus the width of the lasers. So, that's a physical tool that we use. Another thing that we can do is called Cubit Shelving. What Cubit Shelving consists of is taking one of the neighboring qubits that we don't want to be affected, and we excite it to some other state temporarily while we apply a single qubit gate to the target qubit. This way that neighboring qubit is out of the range of frequencies in which it can be influenced. So that's one strategy. Another one is to physically move the neighboring qubits. So to use some type of transport to move the ions away from one another so you can target one without affecting the others. And another one is to use composite pulses. And so this consists of using sort of a sequence of different pulses which correct the errors that occur on the neighboring qubits as you're doing the pulse. So the last question then, what we've seen here so far is how to transition from the excited state to the ground state. So in our block sphere picture, that consists of axes consists of rotations around one axis from the ground to the excited state. But we need rotations around two axes to be able to do arbitrary single qubit gates. Well, recall that in our interaction Hamiltonian, there was this term corresponding to the phase. And this is the phase of the laser. So when implementing a single qubit gates, we can adjust the phase of the laser to be able to do rotations around a second axis in the Bloch sphere. And thus, by controlling the duration of the pulse and the phase of the pulse, we can then implement arbitrary single qubit gates. So we're now going to consider how we can implement two qubit gates. And there exist different ways that two qubit gates can be done. Here we're going to look at the Dirac-Zoller gate. We consider this one because it was the first gate that was proposed for two qubits. This gate launched the field of trapped ion quantum computing, so it's also very significant historically. And also the newer two qubit gates that have been proposed use the same principles in essence of the Dirac-Zoller gate. So the Dirac-Zoller gate operates in 3 stages. So in the very beginning, we have just some superposition state. Where our first qubit, using that 1 there to denote the first qubit, is in some general superposition state. Our second qubit is in some general qubit state, and then our phonon state is just initialized to 0. The first step consists of transferring the quantum info from the first qubit to the phonon. And so we can do that with a red sideband pulse. So recall that a red sideband pulse will couple these states. We're going to do it on the first qubit in the phonon mode. And we're going to do this as a pi pulse. So if you go through the math, there's also going to be a phase here of minus I. The phase will be undone later on, so it's not an issue. So if we go and write out this full state, if we expand it out into 4 terms and implement this red sideband pulse, what we'll have then is the following. So I'm using this notation here. This is just, instead of writing G1 tensor G2 tensor 0 subscript m, I'm just writing GG0. Minus G1. So this term was changed because it has the one with an E here in the 0 state. This one was unchanged, and this one was changed by the red sideband pulse. Okay. The second step is we're going to implement a control Z gate on the space of the second qubit and phonon. So the way we do this is we actually use a different pulse than what we've considered so far. It's just one that couples this state to some other excited state. This is just one of the other electronic states in our system. If we implement a 2 pi pulse, we're going to pick up a 2 pi pulse on the Bloch sphere is equivalent to essentially doing nothing. But in quantum mechanics, as we saw earlier in the course, we pick up a global phase. So we get that. So if we look at which of our four states has the second qubit in the ground state and the phonon mode in the one state, it's just this state here. So the only difference is that this state is going to pick up a phase. The last step is just repeating step one. So again, we do this transition here again with the red sideband pulse. So and what we're left with so if you compare this state here, our final state, with our initial state here, what you'll see is that they're identical up except for this phase here. And so this is the effect of a control Z gate. So a control Z gate in the basis of four states, it leaves three of them unchanged and adds a phase to one of them. So this is the same underlying principle that's used in all other two-qubit gates and trapped ions. We use the phonon mode as an intermediary in which we sort of bus over quantum information between different qubits. So now we're going to consider how measurements are done, a question about scalability, and the effects of noise in trapped ions. So first, regarding measurements, the way measurements are done, so we have our ground state, our excited state, and then some other even further excited state. And ideally it's one that has a very, very short lifetime. What we do is we couple the excited state to this state, and the state gets excited, it then decays, emitting a photon. And we repeat this many, many times, and the photons are detected with a photon detector. As we saw when studying optical qubits, photon detectors aren't perfect, and so we repeat this process for a large window of time. And on average, the two states can be distinguished. So this is known as state-dependent fluorescence. That is likely not how you spell fluorescence, but I'm teaching physics and not spelling. So we have a question here now on scalability. So why can't we just take an ion trap and extend it as long as we need to with thousands and thousands of ions in a very thin and long trap? Well, really the issue comes down to 2 points. One is that two-qubit gates become harder to do, and that we have to deal with greater issues with crosstalk with more qubits. There's been different ideas proposed to avoid these issues, and one is to use a modular structure. So instead of having a single long trap, we have different components of the trap, each of them are different modules, and the challenge then shifts from that of implementing these challenges to being able to do entangling gates between the different modules and to communicate, I guess, in general, between the two modules. Or more than two, the many different modules. So this is still an active area of research on questions regarding the scalability and creating more scalable models for trapped ions. Okay. So one other point to talk about is noise, decoherence. So optical qubits are going to have their coherence time inherently limited by their lifetime, which is on the order of 1 to 10 seconds. However, optical qubits don't have coherence times of that order due to two reasons. So one is that, as mentioned before, optical qubits, they need to implement gates quickly. And when you're doing these fast gates, small phase fluctuations have a significant impact. So there's, from control, you get significant phase errors. The other is fluctuations due to noise in the electromagnetic environment. So because of these, we get coherence times of 10 to 100. I should get that right. Milliseconds. Hyperfine qubits can do a bit better here. They only deal with this second issue. And so because of that, their coherence time is more on 10 to the 3 to 10 to the 5 millisecond range. Now we also have another quantum mode that we use, and that's the motional state, the Phonon mode. So we have to consider errors that can occur here, and the noise that affects that. Here, the predominant source of the error is from heating in the environment, and the heating also being caused by noise in the electromagnetic environment, particularly noise that's close to the frequency of the Phonon mode. So again, noise. What's fairly interesting is that the degree of heating that occurs is many orders of magnitude greater than what is expected from the known sources of heating. So this is actually currently an active area of research to characterize the cause of this heating. And due to its unknown nature, it's known as anomalous heating. So characterizing that and understanding that is a current area of research. Okay, so we've reached the end of the lectures. So I'm just going to do a summary of how the DiVincenzo criteria are satisfied and just briefly talk about the strengths and weaknesses of trapped ion quantum computers. So our qubit with the electronic states of an ion, initialization, is done with Doppler cooling, sideband cooling, and some optical pumping. Control. For 1-qubit gates, we use Rabi oscillations and Raman transitions. For 2-qubit gates, we use the motional mode, for example, such as the CRX gate. There's other gates that are built on that principle. Then for measurement, we have state-dependent fluorescence. Which I still don't know how to spell. And the decoherence times are given in a table in the lecture notes. So you have that to talk about sort of noise and decoherence. So also to wrap up, we're going to talk about the strengths and weaknesses, sort of review things we've said throughout the lecture on this. So one is that the coherence to gate time is incredibly high. So it's the order of 10 to the 6 gates, which, to put it in perspective, that's about 1,000 times bigger than superconducting qubits, which are the next highest. So that's one huge strength. The other one is the gate fidelities. And so single qubit gates have been done up to 0.999 fidelity. And 2-qubit gates have been done with 0.999 fidelity. There's also a table in the lecture notes outlining the fidelity of different gates that have been done. And another point is on the reproducibility of trapped ions. So with other implementations, well, maybe not with all of them, but at least with superconducting qubits, for instance, you have to fabricate the qubit. You have a calcium ion in one lab is going to be the same as a calcium ion, or an identical calcium ion in another lab. So it makes reproducibility easier. However, there's some key weaknesses. One is sort of related to this point, is that the gate times, even though you can do many because of the long coherence times, the gate times are still relatively slow. And so how slow? Well, based on the current state of the art, to factor 1024 bits would take 10 days. If you double that, if you go to 2048, it multiplies by a factor of 10. It's about 100 days. So the gates are slow. That's one point where superconducting qubits has a huge advantage. And the other one is that the number of lasers scales linearly with the size of the trap. So you're going to have an incredible amount of lasers necessary for your quantum computer. So those are sort of two predominant challenges I'll just sort of highlight. And I guess one comment also about industry is that predominantly it's been IonQ that's sort of been leading the charge in this way, and that's sort of a startup company. So that sort of reviews everything we want to mention for trapped ions. If you have any questions, feel free to contact either the TA or myself as well. I'm available. At U Waterloo. And I'll be happy to answer any questions or to chat about anything related to trapped ion quantum computing. Thank you.